Welcome to the lab, everyone. I'm Dr. Kim, and today we're diving into a complete experimental masterclass on exactly how we measure and map out electrochemical corrosion. We're looking at a detailed explainer on electrochemical corrosion studies, literally pulling back the curtain on how scientists test materials long before they ever make it into the real world.
Right, so before a concrete bridge fails, or a medical implant starts corroding inside the human body, we desperately need forensic tools to track this silent killer. And really, that brings us to the core of our experimental journey today. How do we actually test for it? How do we measure it accurately before it's too late? Well, let's find out.
Here's our syllabus for today's masterclass. We'll be covering 1. The basics of electrochemical corrosion. 2. Direct current testing. 3. The power of EIS. 4. Listening to electrochemical noise. And finally, 5. Advanced experimental case studies.
Okay, let's jump right into Section 1, Basics of Electrochemical Corrosion, focusing on the physical electrochemistry interface.
To really understand this electrical process happening right at the interface of a metal and an electrolyte, we've got to start at the absolute beginning. So the very first step in the lab is always measuring the open circuit potential, or EOC. Basically, this is the equilibrium potential a metal naturally assumes when there are zero electrical connections to it. It establishes our crucial baseline before we start forcing any voltages into the system. Now here's the kicker. While we can't actually measure the true corrosion current, which we call Icorr, directly, we can use an instrument called a Potentiostat to polarize the sample and model its behavior. By forcing the potential away from EOC, we get to see what happens. Does an oxide layer form, causing the metal to passivate? Or does the breakdown of those passive films lead to really dangerous, localized pitting corrosion?
Moving right along to Section 2, Direct Current or DC Testing, looking specifically at linear polarization and Tafel analysis.
This is where we use direct current methods to actively push the metal away from its equilibrium just to see how it fights back. Industrial labs rely heavily on standardized DC tests to simulate years of exposure in just a fraction of the time. We've got standard tests for evaluating aerospace alloys in incredibly harsh sulfuric environments, and galvanic tests for multi-part metallic medical implants and simulated body fluids. We have to ensure these bimetallic contacts are completely safe inside our bodies, right?
One of the most common DC methods you'll see is linear polarization resistance, or LPR. By nudging the potential just 10 tiny millivolts in either direction from its open circuit potential, and then measuring the slope of the resulting current curve, we get a rapid, almost completely non-destructive look at general corrosion rates using the Stern-Geary equation.
Now, DC testing is fantastic for general corrosion. It's rapid, real-time, and super easy to analyze. But there's a pretty major limitation here. If your sample has an electrically insulating coating, or if it's sitting in a really low conductivity solution, the DC method kind of falls apart. The measured current ends up capturing the total resistance, including the resistance from the solution itself. This totally muddies our data, because it captures everything instead of just a specific polarization resistance we actually care about.
Which brings us to Section 3, the power of EIS and the alternating current revolution.
To bypass those severe DC limitations, we ditch the static push and use tiny sinusoidal waves across various frequencies instead. By applying an alternating current potential, electrochemical impedance spectroscopy, or EIS, allows us to create an equivalent electrical circuit model. This brilliantly isolates the true, actual polarization resistance from the interference of those pesky insulating coatings or low conductivity solutions.
Before modern computers took over, scientists actually analyzed these Lissajous figures on oscilloscope screens. It's a fascinating way to map the applied sinusoidal voltage signal right against the resulting AC current response. That oval shape essentially shows the phase shift, which was then used to mechanically determine the impedance.
Fast forward to today, and we plot all this data on a Nyquist plot. The x-axis shows the real impedance, and the y-axis shows the imaginary impedance. It's such a clean way to represent the electrochemical circuit as a complex vector with a distinct phase angle, completely separating out those unwanted resistance values we talked about earlier. But there's a fundamental rule you've got to remember with EIS. Electrochemical cells are not linear. Just doubling the voltage won't necessarily double the current. That's exactly why we keep our AC signals incredibly small. We literally have to trick the electrochemical cell into behaving linearly. By looking at a small next portion of the curve, it acts in a pseudo-linear way, and that's what allows us to properly analyze the data without distorting the whole system.
All right, on to Section 4, Listening to Electrochemical Noise, Uncovering Stochastic Processes.
This part is just fascinating. What if we don't apply any external voltage or current at all? Enter electrochemical noise, or ECN, by simply monitoring the naturally occurring low-level fluctuations of the corrosion potential. We're talking perturbations of less than 1 millivolt between two identical electrodes. We can mechanically determine the type and speed of localized corrosion just by observing its natural electrical noise.
So what's actually causing this noise? Well, it's driven by macroscopic stochastic phenomena. These are random, unpredictable chemical events happening constantly at the surface. We're talking about partial Faradaic current absorption and desorption, rapid changes in surface coverage, or even random localized corrosion cracking and mechanical erosion. It's kind of like we're listening to the microscopic pops and crackles of a metal degrading in real time.
Let's move to our final segment, Section 5, Advanced Experimental Case Studies, featuring the wire beam electrode, or WBE.
For our grand finale, researchers took a really ingenious approach. Instead of using one solid block of metal, they embedded 100 tiny carbon steel wires into an epoxy resin to create a wire beam electrode. By immersing this multi-wire block into a highly corrosive Evans solution, they were able to map local galvanic currents and measure the distinct potential of each individual wire over hours of exposure to perfectly pinpoint metastable pit growth.
When you set up the physical wiring rig for the WBE and hook it up to multiplexers, you get something incredible. Actual visual maps of the galvanic current distributions. You can literally see the exact moments local anodes form, giving us a real-time visual map of the instantaneous corrosion dissolution rate. It is a total game changer. This experimental method is absolutely groundbreaking. It pinpoints the breakdown of passive films and identifies rapid potential changes towards less negative directions, essentially capturing those crucial electrical spikes. And because they validated it physically using a Nikon EpiPhoto 20 microscope, it finally solves long-standing controversies in the field around exactly how, when, and where a localized pit nucleates.
Armed with these incredible experimental tools, the future of civil engineering looks brilliant. As artificial intelligence continues to integrate with these live monitoring techniques like EIS and electrochemical noise, it leaves us with a pretty provocative thought. Will intermittent electrochemical control and smart systems permanently eradicate structural corrosion in things like our concrete bridges? Will unexpected corrosion soon be a thing of the past? I'm Dr. Chem, and I really hope this explainer sparked your curiosity about the silent electrical world of corrosion. Keep exploring, and I'll catch you next time.